Mersenne primes. One unsolved problem in mathematics concerns whether or not there are infinitely many Mersenne primes. In order to understand what a Mersenne prime is, consider the expression 2 to the n minus 1 for a non-negative integer n. A number of this form is called a Mersenne number. These are named after Mersenne, a French mathematician. For some prime number values of p, the value of the whole expression is also a prime number. For example, plugging in p equals 2, the expression evaluates to 2 to the power of 2 minus 1, which is the prime number 3. A prime number of the form 2 to the p minus 1, where p is also a prime number, is known as a Mersenne prime. As it turns out, if p is a non-negative integer, then it must be a prime number for 2 to the p minus 1 to equal a prime number. However, there are some prime number values of p that do not produce a prime number. For example, if p equals 11, then the expression evaluates to 2047, which is a composite number with factors 1, 23, 89, and itself. As a result, you can't just plug in Mersenne primes themselves for p in order to keep getting new Mersenne primes forever. Indeed, there is no consistent, reliable formula for generating Mersenne primes. Finding new ones primarily comes down to using guess-and-check computer algorithms. Currently, only 51 Mersenne primes are known, with the largest one being 2 to the power of 82,589,933 minus 1. Incidentally, this is also the largest known prime number overall. Based on our computations, Mersenne primes seem to be exceedingly rare among the Mersenne numbers. However, whether or not they eventually stop remains a mystery. Perfect numbers. A perfect number is a positive integer equaling the sum of its proper divisors, which are the number's divisors other than the number itself. For example, the proper divisors of 6 are 1, 2, and 3, and 1 plus 2 plus 3 equals 6, so 6 is a perfect number. The next few perfect numbers are 28, 496, and 8128. There are two main unsolved problems relating to the perfect numbers. One of them asks whether or not there are any odd perfect numbers. Odd numbers tend to miss out on divisors thanks to not being divisible by 2, or by any multiple thereof. Currently, all of the 51 known perfect numbers are even, not odd. However, much progress has been made in regards to this problem. Mathematicians have come up with an incredibly long and strict list of rules that an odd perfect number must follow, if such a number exists at all. Going over the whole list would take all day, but needless to say, odd perfect numbers must be either very rare and special, or completely non-existent. In general, mathematicians guess that the latter is true. The set of conditions required for an odd perfect number just seems far too restrictive. As English mathematician James Joseph Sylvester put it, a prolonged meditation on the subject has satisfied me that the existence of any one such odd perfect number, its escape, so to say, from the complex web of conditions which hem it in on all sides, would be little short of a miracle. The second problem about perfect numbers asks whether there exist infinitely many of them. There are some known facts related to this problem. For example, the Mersenne primes are closely related to the perfect numbers. Consider the expression 2 to the power of quantity p minus 1 times quantity 2 to the power of p minus 1, where 2 to the power of p minus 1 is a Mersenne prime. In that case, no matter what Mersenne prime we have, this expression always gives us an even perfect number. If p equals 2, our Mersenne prime is 3, and this expression evaluates to 6. If p equals 3, our Mersenne prime is 7, and this expression evaluates to 28, and so on. This fact was proven by the Greek mathematician Euclid. Conversely, given any even perfect number, we can find the Mersenne prime that would have yielded it when using this expression. In other words, there exists a bijection, a one-to-one correspondence, between the set of perfect numbers and the set of Mersenne primes. This was proven by Swiss mathematician Leonhard Euler. In honor of Euclid and Euler, this theorem is called the Euclid-Euler theorem. Because of it, as soon as anyone finds out whether or not there are infinitely many Mersenne primes, we will also know whether or not there are infinitely many even perfect numbers, and vice versa. Rational distance problem. In geometry, a plane is a flat 2D space that extends to infinity in all directions. Basically, an infinitely large sheet of paper. Imagine a unit square, a square with sides length equal to 1 unit, living in this space. The rational distance problem asks, does there exist a point in the plane a rational distance away from every vertex of a unit square? To elaborate, suppose that this plane has a Cartesian coordinate system, the usual xy coordinates you may be familiar with. For simplicity, we'll place this square's vertices at 0, 0, 0, 1, 1, 0, and 1, 1. Now, for this problem, pick any point in this plane. Calculate the distance between this point and each vertex of the unit square. The distance between 2 points x1, y1, and x2, y2 can be calculated using the distance formula. D equals square root quantity x2 minus x1 squared plus quantity y2 minus y1 squared. For the chosen point and the 4 vertices of the unit square, the goal is to have every one of the 4 distances be a rational number. Despite the apparent simplicity of this task, no one has succeeded at it yet, nor has anyone proven that it is impossible. One option is to examine regular polygons of unit side length other than the square. The simplest example is the equilateral triangle, for which we know that a point can be chosen to result in all distances being rational. This also holds for the regular hexagon. However, the answer for squares, octagons, 12gons, and 24gons remains unknown. All remaining regular polygons, the answer is known to be no. If you want to try solving some math problems yourself, you'll probably want to train your mathematical skills. For that, there's no better place to start than today's sponsor, Brilliant. Brilliant is a learning platform that emphasizes hands-on education. Lessons let you play with the concepts yourself rather than just seeing them, a method shown to be far more effective than simple lecture videos. Brilliant features thousands of interactive lessons in math, AI, programming, and data analysis, all created by top teachers, researchers, and professionals from universities and companies like MIT, Caltech, Duke, Google, and Microsoft. With simple short lessons you can do at your own pace, you can build your knowledge every day. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/thoughtthrill or click on the link in the description. You'll also get 20% off an annual premium subscription. Moving sofa problem. Imagine a hallway 1 unit wide with a 90-degree L-shaped bend. You want to slide some kind of shape, let's say it's a sofa, from one side of this bend to the other. What is the maximum possible area that such a shape can have? Whatever this maximum value for the area is, it is called the sofa constant. We can start with a half disk of unit radius, where a disk is the region enclosed by a circle. The unit disk has an area of pi, and half of that is pi over 2, about 1.57. This gives us a simple lower bound on the sofa constant, but we can do better. In 1968, British mathematician John Hammersley proposed a sofa roughly in the shape of a telephone handset. This sofa has an area of pi over 2 plus 2 over pi, about 2.207. Later sofas have surpassed this number, with the current record being 2.2195, believed to be close to the true sofa constant. Upper bounds on the sofa constant have also been obtained. Hammersley found an upper bound of 2 times square root 2, about 2.828. Later in 2018, Yoav Kallis and Dan Romick lowered this to about 2.37. Their approach involved using computers to rotate the hallway around the sofa, not the other way around. Inscribed square problem. A curve is closed if it loops back on itself, and it is simple if it doesn't cross over itself. A simple closed curve in a plane is called a Jordan curve. A polygon is inscribed in a curve if all of its vertices are on the curve. The question is, does every Jordan curve have an inscribed square? We can start with some simple examples of Jordan curves. A circle is a Jordan curve, and it has infinitely many possible inscribed squares. A square itself is also a Jordan curve, and infinitely many inscribed squares can be found in this curve as well. As for triangles, an obtuse triangle has exactly 1 inscribed square, a right triangle has 2, and an acute triangle has 3. In the general case, the problem has proven to be difficult. However, some special cases have been proven. For example, in 1916, Arnold Emch showed that a piecewise analytic curve must have inscribed rhombuses, and at least one of these rhombuses is a square. Also, it has been shown that all symmetric curves have at least one inscribed square. Another case involves an annulus, the region bounded by two concentric circles, where the outer radius is at most 1 plus square root 2 times the inner radius. If the Jordan curve is inscribed in such an annulus, and separates the annulus's inner and outer circles, then a sequence of squares leading to a square inscribed in the Jordan curve can be found. Ramsey theory problem. Ramsey theory is a branch of combinatorics named after British mathematician and philosopher Frank P. Ramsey. It is primarily focused on the size of mathematical structures. One problem is as follows. Consider the vertices of an n-dimensional hypercube. 1D is a line segment, 2D is a square, 3D is a cube, and so on. Draw edges from every vertex to every other vertex, forming what is known as a complete graph. Each edge can be colored either red or blue. Depending on the number of dimensions n, it may be possible to color these edges so that if you take the complete graph of 4 vertices in the same plane, not all the edges are the same color. This complete graph can be visualized as a square with the diagonals drawn in. What is the smallest number of dimensions in which this is possible? Lower and upper bounds for this problem have been obtained. In 1971, American mathematicians Ronald Graham and Bruce Lee Rothschild found a lower bound of 6. In 2003, Jeffrey Exo improved this to 11, which was later improved to 13 by Jerome Barkley in 2008. As for the upper bound, it can only be reasonably expressed using operations known as the hyperoperations, which extend the usual operations of addition, multiplication, and exponentiation. The most famous upper bound found for this problem is a number called Graham's number, which once held the world record for the largest number used in a serious mathematical proof. Graham's number is too large for an ordinary decimal representation of it to fit into the observable universe, even if each digit is only 1 Planck volume, and even that astronomically undersells its size. In any case, the current upper bound is a much smaller number that looks like this. Square packing. A unit square is a square with a side length of 1 unit. Suppose you have a collection of some number of unit squares. We'll call this number n. You want to pack all these squares into a large square enclosure with no overlap. For a given number of unit squares, n, what is the smallest enclosure you can make? We will express the size of the enclosure using its side length a. This problem is known as the square packing problem. The most trivial case is when n is a square number, 1, 4, 9, etc. Then you can simply arrange all of your unit squares into a grid pattern with a square border, and this border is the enclosure, having side length square root of n. Many other values of n yield simple solutions as well, where the squares are similarly aligned to the grid, like with 2 or 3 squares. 5 squares is an interesting case. 1 square is placed at a 45-degree angle from the grid, and the other 4 are placed around it, resulting in an enclosure side length of a equals 2 plus 1 over the square root of 2, about 2.707. The solution for 10 squares is simply an extension of the solution for 5 squares. Despite the square packing problem's apparent simplicity, much about it is still unknown. It remains unsolved for some rather small values of n, the smallest 2 being n equals 11 and n equals 17. Approximations have been obtained in these cases, those being a approximately equal to 3.88 and a equals approximately 4.68, respectively, and giving some bizarre-looking packings. Bellman's lost in a forest problem. Imagine being lost in a forest. You don't know where you are or what direction you're facing, but you do know the exact shape and size of the forest. What is the best path to take to ensure the lowest escape time in the worst-case scenario? This problem was first posed by American mathematician Richard E. Bellman. It was originally about unbounded regions, like an infinite strip between 2 parallel lines, or a half-plane, which is the region of a plane on one side of a line. However, mathematicians later investigated bounded regions as well. There is no known general solution to this problem, Such a solution would be some kind of algorithm where you plug in the forest's shape and size, and it gives you back the best path of escape. However, some specific cases have been proven. One possibility is that a forest is fat, meaning that the best escape route is a linear path. Just walk in a straight line. For instance, every regular polygon with at least 4 sides is fat. If you let the number of sides of a regular polygon approach infinity, the sequence of shapes approaches a circle, so a circle is also fat. The only regular polygon with no known solution is the equilateral triangle. The lost in a forest problem is part of a group of optimization problems in geometry that have practical uses when it comes to search strategies. However, there do not seem to be any real-world applications. Important note: this applies even if you are actually lost in a forest. If this happens, you should usually stay put and wait for searchers. This video is not a survival guide, so for more information, consult other sources. Ulam's packing conjecture. As another packing problem, though this time in 3 dimensions instead of 2, Ulam's packing conjecture concerns the packing of identical balls in a 3-dimensional space. To begin, we must define convex solids. A convex solid is a solid figure where any pair of points in the solid is connected by a line segment that is also completely contained in the solid. For instance, a ball is a convex solid, because if you choose any 2 points inside the ball and draw the line segment between them, the line segment will also be entirely inside the ball. Contrarily, a solid torus, a donut shape, is not convex because, for example, the line segment between 2 opposite points of the solid torus will pass through empty space. Now, imagine taking a bunch of identical convex solids and using them to fill a space, packing them as tightly as possible with no overlap. The packing density is the proportion of the space that is occupied by the solids. If the solids are packed as tightly as they can be, their density is called the optimal packing density. Of course, we can't take the volume of infinitely many solids and divide it by the volume of the infinite space they occupy. Instead, we will consider the proportion of occupied volume in a very large space, then take the limit as the volume of this space approaches infinity. Ulam's packing conjecture, named for Polish mathematician Stanislaw Ulam, and where conjecture is math speak for guess, states that the ball has the smallest optimal packing density of any convex solid. In other words, if you want to fill up a space with a bunch of identical solids, then balls are the least efficient way to do it. Another conjecture called the Kepler conjecture says that the optimal packing density for balls is pi over 3 times the square root of 2, or tau over 6 times the square root of 2 if you prefer, approximately 74%. As for Ulam's packing conjecture, experimenting with many different convex solids has given confidence that the conjecture is true, but no proof has been devised. Lesbegue's universal covering problem. You may already know what the diameter of a circle is. It's just the largest possible distance from one point on the circle to another. Similarly, the diameter of any shape can be defined as the largest possible distance from one point on that shape to another. For instance, the diameter of a unit square is square root of 2, since that's the distance between opposite vertices of the unit square, and those are the points of the square that are farthest apart. Let's say we're in 2D, and we have some kind of convex shape that can contain any shape with a diameter of 1. Let's call the first shape the cover, since it can be used to cover up any of the diameter 1 shapes. The diameter 1 shapes can be translated, rotated, and reflected, slid, spun around, and flipped, respectively, to fit in the cover. Lesbegue's universal covering problem asks, what is the smallest area that this cover can have? The problem is named after French mathematician Henri Lesbegue, who first posed it in 1914 in a letter to Hungarian-Danish mathematician Gyula Pál. Pál analyzed the problem in a 1920 paper, and his analysis involved curves of constant width. A curve of constant width is a shape with the same width in all directions. The most well-known example is the circle, but there are infinitely many more, such as the Rayleigh triangle. The paper showed that if you simply find a cover for all curves of constant width with a diameter of 1, then it will also cover every possible shape of diameter 1. Pál also showed his best solution for such a cover, a hexagon with 2 corners snipped off. Its area is 2 minus 2 over square root of 3, about 0.845. This upper bound was improved to about 0.88414 in 1936, then to about 0.88409 in 2018. The best known lower bound is about 0.832, meaning no cover could ever have an area less than this. Moser's worm problem. Imagine a curve in the plane with a length of 1. You could think of it as a worm, or a piece of string. Similar to Lebegue's universal covering problem, Moser's worm problem asks for the smallest area of a region that can contain every such curve. Once again, translations, rotations, and reflections are allowed. For this problem, it is relatively easy to find some simple covers. One example is a disk of radius 1/2, where any curve of length 1 can be covered by placing its midpoint at the disk's center. This disk has an area of pi over 4, about 0.785. An even smaller cover is a rhombus with angle measures of 60 degrees and 120 degrees, and a long diagonal that's 1 unit long with an area of 1 over square root of 3, about 0.577. And no, this is not the Euler-Mascheroni constant. When approaching this problem, one possibility to consider is that a solution doesn't even exist. For instance, what if we found out that a cover can be constructed with a given area if, and only if, that area is greater than some number, say 0.5. In that case, our cover's area could be 0.51, or 0.501, and so on, but never exactly 0.5. Since you could just keep getting closer and closer to 0.5, approaching it without reaching it, there would be no smallest area. However, if we only consider convex covers, then the Blaschke selection theorem tells us that a smallest convex cover must exist. Though the solution to this problem is unknown, some bounds have been obtained, both in the general case and the convex case. The general case has an upper bound of about 0.26, while the convex case has a lower bound of about 0.23 and an upper bound of about 0.27. A 30-degree unit radius circular sector with an area of pi over 12, about 0.2618, was conjectured to be a convex cover by John Wetzel in the 1970s. Proofs were independently claimed in 2017 and 2021. If these are confirmed, this will be a new upper bound for the area of a convex cover. Kobon triangle problem. If you draw 3 lines, as in infinite lines, not line segments, in a plane, you can make them form a triangle. If you draw 4 lines in a plane, you can make them form a maximum of 2 triangles. For 5 lines, the maximum jumps up to 5 triangles. So in general, for k lines, what is the largest possible number of non-overlapping triangles formed? N of k. This problem is called Kobon's triangle problem, named after Kobon Fujimura. A known upper bound for n of k exists, floor quantity k times quantity k minus 2 over 3, found by Saburo Tamura. Here, the floor function takes in a number and returns the greatest integer less than or equal to that number. Basically, it rounds down. For instance, if k equals 4, this expression can be evaluated like this. Exact solutions are known for numbers of lines from 3 to 9, as well as 13, 15, and 17. In the case of the first unsolved number of lines, k equals 10, the upper bound is 26 triangles, whereas the best solution obtained so far is 25.
The kissing number problem. A broad category of problems in math are called the sphere packing problems. They range from pure math to practical stuff, like figuring out how to stack many spheres in a given space, like fruit at the grocery store. Some of these problems have solutions, but others, like the kissing number problem, are still tricky. When a bunch of spheres are packed in some region, each sphere has a kissing number, which is the number of other spheres it's touching. If you're touching 5 neighboring spheres, then your kissing number is 5. Nothing tricky. A packed bunch of spheres will have an average kissing number, which helps mathematically describe the situation. But a basic question about the kissing number stands unanswered. A one-dimensional thing is a line, and a two-dimensional thing is a plane. For these low numbers, mathematicians have proven the maximum possible kissing number for spheres of that many dimensions. It's 2 when you're on a 1D line, one sphere to your left and the other to your right. There's proof of an exact number for 3 dimensions, although that took until the 1950s. Beyond 3 dimensions, the kissing problem is mostly unsolved. Mathematicians have slowly whittled the possibilities to fairly narrow ranges for up to 24 dimensions, with a few exactly known, as you can see on this chart. For larger numbers or a general form, the problem is wide open. There are several hurdles to a full solution, including computational limitations. So expect incremental progress on this problem for years to come. The Goldbach Conjecture, one of the greatest unsolved mysteries in math, is also very easy to write. Goldbach's conjecture is, every even number greater than 2 is the sum of 2 primes. You check this in your head for small numbers. 18 is 13 plus 5, and 42 is 23 plus 19. Computers have checked the conjecture for numbers up to some magnitude, but we need proof for all natural numbers. Goldbach's conjecture precipitated from letters in 1742 between German mathematician Christian Goldbach and legendary Swiss mathematician Leonhard Euler, considered one of the greatest in math history. As Euler put it, I regard it as a completely certain theorem, although I cannot prove it. Euler may have sensed what makes this problem counterintuitively hard to solve. When you look at larger numbers, they have more ways of being written as sums of primes, not less. Like how 3 plus 5 is the only way to break 8 into 2 primes, but 42 can be broken into 5 plus 37, 11 plus 31, 13 plus 29, and 19 plus 23. So it feels like Goldbach's conjecture is an understatement for very large numbers. Still, a proof of the conjecture for all numbers eludes mathematicians to this day. It stands as one of the oldest open questions in all of math. Collatz Conjecture. In September 2019, news broke regarding progress on this 82-year-old question, thanks to genius mathematician Terence Tao. And while the story of Tao's breakthrough is promising, the problem isn't fully solved yet. A Collatz conjecture is all about a function f of n, which takes even numbers and cuts them in half, while odd numbers get tripled and then added to 1. Take any natural number, apply f, then apply f again and again. You eventually land on 1 for every number we've ever checked. The conjecture is that this is true for all natural numbers, positive integers from 1 through infinity. Tao's recent work is a near solution to the Collatz conjecture in some subtle ways, but he most likely can't adapt his methods to yield a complete solution to the problem, as Tao subsequently explained. So, we might be working on it for decades longer. The conjecture lives in the math discipline known as dynamical systems, or the study of situations that change over time in semi-predictable ways. It looks like a simple, innocuous question, but that's what makes it special. Why is such a basic question so hard to answer? It serves as a benchmark for our understanding. Once we solve it, then we can proceed to much more complicated matters. The study of dynamical systems could become more robust than anyone today could imagine, but we'll need to solve the Collatz conjecture for the subject to flourish, the twin prime conjecture. Together with Goldbach's, the twin prime conjecture is the most famous in number theory, or the study of natural numbers and their properties, frequently involving prime numbers. Since you've known these numbers since grade school, stating the conjectures is easy. When 2 primes have a difference of 2, they're called twin primes. So 11 and 13 are twin primes, as are 599 and 601. Now, it's a day 1 number theory fact that there are infinitely many prime numbers. So, are there infinitely many twin primes? The twin prime conjecture says yes. Let's go a bit deeper. The first in a pair of twin primes is, with one exception, always 1 less than a multiple of 6. And so, the second twin prime is always 1 more than a multiple of 6. You can understand why if you're ready to follow a bit of heady number theory. All primes after 2 are odd. Even numbers are always 0, 2, or 4 more than a multiple of 6, while odd numbers are always 1, 3, or 5 more than a multiple of 6. Well, one of those 3 possibilities for odd numbers causes an issue. If a number is 3 more than a multiple of 6, then it has a factor of 3. Having a factor of 3 means a number isn't prime, with the sole exception of 3 itself. And that's why every third odd number can't be prime. How's your head after hearing this? Now imagine the headaches of everyone who has tried to solve this problem in the last 170 years. The good news is that we've made some promising progress in the last decade. Mathematicians have managed to tackle closer and closer versions of the twin prime conjecture. This was their idea? Trouble proving there are infinitely many primes with a difference of 2? How about proving there are infinitely many primes with a difference of 70 million? That was cleverly proven in 2013 by Yitong Zhang at the University of New Hampshire. For the last 6 years, mathematicians have been improving that number in Zhang's proof, from millions down to hundreds. Taking it down all the way to 2 will be the solution to the twin prime conjecture. The closest we've come, given some subtle technical assumptions, is 6. Time will tell if the last step from 6 to 2 is right around the corner, or if that last part will challenge mathematicians for decades longer. The unknotting problem. The simplest version of the unknotting problem has been solved, so there's already some success with this story. Solving the full version of the problem will be an even bigger triumph. You probably haven't heard of the math subject knot theory. It's taught in virtually no high schools and few colleges. The idea is to try and apply formal math ideas, like proofs, to knots, like, well, what you tie your shoes with. For example, you might know how to tie a square knot and a granny knot. They have the same steps except that one twist is reversed from the square knot to the granny knot. But can you prove that those knots are different? Well, knot theorists can. Knot theorists' holy grail problem was an algorithm to identify if some tangled mess is truly knotted, or if it can be disentangled to nothing. The good news is that this has been accomplished. Several computer algorithms for this have been written in the last 20 years, and some of them even animate the process. But the unknotting problem remains computational. In technical terms, it's known that the unknotting problem is in NEP, while we don't know if it's in P. That roughly means that we know our algorithms are capable of unknotting knots of any complexity, but that as they get more complicated, it starts to take an impossibly long time, for now. If someone comes up with an algorithm that can unknot any knot in what's called polynomial time, that will put the unknotting problem fully to rest. On the flip side, someone could prove that isn't possible, and that the unknotting problem's computational intensity is unavoidably profound. Eventually, we'll find out. The enigma of pi plus e. Given everything we know about two of math's most famous constants, pi and e, it's a bit surprising how lost we are when they're added together. This mystery is all about algebraic real numbers. The definition: a real number is algebraic if it's the root of some polynomial with integer coefficients. For example, x squared minus 6 is a polynomial with integer coefficients, since 1 and negative 6 are integers. The roots of x squared minus 6 equals 0 are x equals square root of 6 and x equals negative square root of 6. So that means square root of 6 and negative square root of 6 are algebraic numbers. All rational numbers and roots of rational numbers are algebraic. So it might feel like most real numbers are algebraic. Turns out, it's actually the opposite. The antonym to algebraic is transcendental, and it turns out almost all real numbers are transcendental, for certain mathematical meanings of almost all. So who's algebraic and who's transcendental? The real number pi goes back to ancient math, while the number e has been around since the 17th century. You've probably heard of both, and you'd think we know the answer to every basic question to be asked about them, right? Well, we do know that both pi and e are transcendental, but somehow it's unknown whether pi plus e is algebraic or transcendental. Similarly, we don't know about pi times e, pi over e, and other simple combinations of them. So there are incredibly basic questions about numbers we've known for millennia that still remain mysterious. Birch and Swinnerton-Dyer conjecture. The Birch and Swinnerton-Dyer conjecture is another of the 6 unsolved Millennium Prize problems, and it's the only other one we can remotely describe in plain English. This conjecture involves the math topic known as elliptic curves. In a nutshell, an elliptic curve is a special kind of function. They take the unthreatening-looking form y squared equals x cubed plus ax plus b. It turns out functions like this have certain properties that cast insight into math topics like algebra and number theory. British mathematicians Brian Birch and Peter Swinnerton-Dyer developed their conjecture in the 1960s. Its exact statement is very technical and has evolved over the years. One of the mathematicians who has worked on refining and understanding this conjecture is Andrew Wiles, who's famous for proving Fermat's last theorem, Riemann Hypothesis. Today's mathematicians would probably agree that the Riemann Hypothesis is the most significant open problem in all of math. It's one of the 7 Millennium Prize problems, with 1 million reward for its solution. It has implications deep into various branches of math, but it's also simple enough that we can explain the basic idea right here. There is a function called the Riemann zeta function. For each s, this function gives an infinite sum, which takes some basic calculus to approach for even the simplest values of s. For example, if s equals 2, then zeta of s is the well-known series, which strangely adds up to exactly pi squared divided by 6. When s is a complex number, one that looks like a plus b times I, using the imaginary number I, finding zeta of s gets tricky. So tricky, in fact, that it's become the ultimate math question. Specifically, the Riemann hypothesis is about when zeta of s equals 0. The official statement is, every non-trivial zero of the Riemann zeta function has real part 1/2. On the plane of complex numbers, this means the function has a certain behavior along a special vertical line. The hypothesis is that the behavior continues along that line infinitely. The hypothesis and the zeta function come from German mathematician Bernhard Riemann, who described them in 1859. Riemann developed them while studying prime numbers and their distribution. Our understanding of prime numbers has flourished in the 160 years since, and Riemann would never have imagined the power of supercomputers. But lacking a solution to the Riemann hypothesis is a major setback. If the Riemann hypothesis were solved tomorrow, it would unlock an avalanche of further progress. It would be huge news throughout the subjects of number theory and analysis. Until then, the Riemann hypothesis remains one of the largest dams to the river of math research. The lonely runner conjecture. Assume there are some kids running around a circular track. Each kid runs at a different speed. Now, if a kid gets far enough away from all the other kids, we say that kid is lonely. This idea is called the lonely runner conjecture. It says that every kid running will become lonely at some point. If there's only one kid running, it's easy because they're always lonely since no one else is there. With two kids, it's also simple. We just watch how fast they run. By pretending one kid is standing still, we can see when the other kid gets lonely. For 3, 4, 5, 6, and 7 kids, smart people have already figured out that each kid will become lonely at some point. But for more than 7 kids, we're still not sure. There have been some guesses and ideas, like looking at really big groups of kids running at different speeds, but the problem hasn't been completely solved yet. Is gamma rational? This is another easy-to-write problem, but hard to solve. All you need to recall is the definition of rational numbers. Rational numbers can be written in the form p over q, where p and q are integers. So, 42 and -11/3 are rational, while pi and the square root of 2 are not. It's a very basic property, so you'd think we can easily tell when a number is rational or not, right? Meet the Euler-Mascheroni. It's a real number, approximately 0.5772, with a closed form that's not terribly ugly. The sleek way of putting words to those symbols is gamma is the limit of the difference of the harmonic series and the natural log. So it's a combination of two very well understood mathematical objects. It has other neat closed forms and appears in hundreds of formulas. But somehow, we don't even know if gamma is rational. People have calculated it to 500 billion digits, yet nobody can prove if it's rational or not. The popular prediction is that gamma is irrational. Along with our previous example pi plus e, we have another question of a simple property for a well-known number, and we can't even answer it. That's it for today. If you enjoyed exploring these mysteries with me, please like and subscribe. Your support means a lot.